Welcome back, dear friends. Now we're going to talk freely and openly about a discovery that appeared in the press which said that our universe, attention, our universe, might be part of a black hole. We would actually be inside a black hole. The whole universe, with all the stars in the sky, with all the galaxies, can you imagine? This news caught my attention because it was related to a recent discovery, namely that the James Webb Space Telescope, which, as you know, was recently launched into space, discovered that there is a preferential direction for galaxy rotation. Specifically, more than 50% of elliptical galaxies rotate in the opposite direction to the one in which the Milky Way rotates. And this recent discovery by James Webb has triggered, so to speak, a wave of reactions, and one of them is this. This would prove that our universe is inside a black hole. Well, I hope the topic is interesting enough for you to stay with me until the end, especially since I will try to speak freely. I've realized something. Honestly, I watched others who make unscripted videos. Yes, I watched Sabine German, I watched Dragos Patraru. Yes, indeed, when you talk about politics, topics always come up and you can move from one to another very quickly. When it comes to science, attention, this is the second time I'm trying to make a video speaking freely about a science topic. Although I had another attempt in between. And that attempt didn't work out. Why didn't it work out? Because there are so many things to talk about. So I started writing down those ideas, and then, guess what? There were so many ideas that I had already written 300 words of that text, just from the ideas. So I decided to keep going and write a text I could read as usual. Now, I'll try not to do that. I have here a list of a few ideas. And I say, let's get started. And I really ask you to watch until the end, because it helps me out somehow. Because, yes sir, how did people come up with the idea that our universe might be inside a black hole? Alright, let's start with this image that I'm looking at too, which is a picture taken by the James Webb Telescope. Here we see a tiny portion of the sky, a really small part of it. And yet, you can see a lot of galaxies. Usually they're called deep field images, meaning you can see galaxies that are very far away. I don't know exactly what distances we're talking about here, but I guess we're talking about hundreds of millions of light years away. And I made a post on Facebook the first time I started working on this article because I said to myself, man, this is pure poetry. Leaving aside the technical side. Do you realize how vast this universe is? Do you realize that a single galaxy we're looking at has hundreds of millions, no billions, even hundreds of billions of stars? And maybe life, or even civilizations, have emerged on some of those planets. Aliens. Maybe there are some alien eyes out there looking toward us. Maybe inside the supermassive black holes. Yeah? Inside those galaxies, maybe those interiors are the portal to other universes, just like they say today. So yeah, I sat and admired the picture before getting to the technical part. Wait, what's the technical part? First, let's look at the picture. We see galaxies, spiral, or spirals. I think it's even better to say spiral galaxies. Some of them are circled in red, others in blue. The galaxies that are circled in red, they rotate in the same direction as our galaxy, the Milky Way. Imagine the galaxies this way. Let's place them in the same plane for simplicity. The red ones rotate in the same direction as our galaxy, and the blue ones rotate in the opposite direction. Of course, this is just an average, because galaxies can be oriented in different directions. And you can see it in the picture. There are several galaxies circled in blue. That means there are more galaxies in the universe that rotate in the opposite direction to our galaxy. By about 50%. It's something the authors of the article say, hey, you can even see this visually. So why is it like this, sir? I mean, why is it? We expected the universe to be isotropic with all galaxies moving in the same direction. Why would there be a preferred direction for the rotation of galaxies? Well, and this is where we get to the main idea. Why is there a preferred direction for galaxies? The article mentions that maybe it's about the way galaxies are oriented, meaning, in other words, there's a mechanism in galaxy formation that somehow selects a preferred direction. There's also talk about another thing, that maybe there's a measurement error because our galaxy is rotating and maybe they didn't apply the rotation corrections properly. But putting these things aside, another idea is indeed mentioned that suggests this rotation existed even at the Big Bang. In other words, when the universe was formed from the Big Bang, matter had a preferred direction, which is later reflected in the rotation of galaxies. I thought of two examples that I can give. One is the water that flows down the sink and swirls. And often you've seen that if there's something floating on the water, that piece also starts to spin. And that rotation, being carried by the water, yes, it has the same direction of rotation as the water in the larger whirlpool. In other words, if there's a bigger whirlpool, just like they say there was at the Big Bang, that whirlpool set the direction of rotation of the galaxies. Not all galaxies. Statistically, about 50% more. I forgot to mention another possibility. A colleague I spoke with said, "Hey Christy, they might have looked at too small a portion of the sky, because if they looked at too big a piece of the sky, they'd still get half and half." The second example I thought of is the formation of the solar system, meaning the protoplanetary disk. That is, we have the sun. We have the initial gas, helium, hydrogen, from which the planets are later formed, the gas giants, and then from the atoms that are there, the rocky planets are also formed. Well, and this protoplanetary disk revolves around the sun and spins in the same direction as the sun. Well, when the planets are formed, the planets somehow acquire rotational angular momentum in the same direction as the protoplanetary disk. So the result is that we expect all the planets to move in the same direction. And that's what we see here. They move in the same direction, but at the same time. And they also spin around their own axis in the same direction. And that's also true except for the planet Uranus, because Uranus was hit by a possible asteroid that tilted it. And I think there's also an issue with Mercury, because Mercury is locked, if I'm not mistaken, relative to the sun's rotation. I should check that. But most of the planets have a rotation in the same direction, right? Because that rotation comes from the rotation of the protoplanetary disk. And that's how it would have happened at the Big Bang too. The universe would have been rotating and would have imprinted that rotation, would have imprinted it on the elliptical galaxies that formed in it. Now we would also need a model to see how the universe could start rotating after the Big Bang. And that article from space.com, not the original article, refers to a Polish physicist who is now a professor in the United States, whose name is Poplawski. And this Poplawski has a theory that says exactly this. And his theory is based on a modified version of Einstein's general theory of relativity, a theory called the Einstein-Cartan theory, and which takes into account the torsion of space. Let's get into this a bit here, because, to be honest, I didn't know about this extension, the extension of the theory of relativity, and in this case, I really haven't done the equations. In my book, Physics Explained, I have the equations from the theory of relativity, and there you can see the theory of relativity, the curvature of space and time. It is based on the energy-momentum tensor. So, what interests us about matter in the classical theory of relativity are just two elements. What is the energy density and what is the momentum density of matter? Then we plug in the equations and see which universes result. And Einstein plugged in these equations, and one of the solutions was the Einstein-Rosen bridge. That is a kind of wormhole where on one side you have a black hole, so basically you have the matter collapses toward a singularity, but then that singularity opens up into a white hole. And that's, well, the Einstein-Rosen bridge, based on the theory of relativity, Einstein's general theory. So in Einstein's theory, you start from the energy momentum tensor. In the Einstein-Cartan theory, so the extension of Einstein's theory, another element is added, namely what they call the torsion of space. Now, Cartan was a mathematician and he made an extension of curved spaces that Riemann had created. Because the theory of general relativity is based on Riemannian spaces, on curved Riemannian spaces, and Cartan extends these curved Riemannian spaces, so Einstein-Cartan is an extension of the theory of general relativity. And I tried to quickly look over that torsion, but I'll be honest with you, I haven't done those equations, so I wouldn't be able to understand them. Unfortunately, I could only describe and reproduce what I've read elsewhere. It would have been really nice to go through those equations, but I don't know. Anyway, it's just an extension of the theory of relativity, but maybe it's the right extension. And why do I say maybe it's the right extension? Because I've read words of praise about this extension of the theory of relativity, in which they say this: Sir, if we take this Einstein-Cartan theory, so where we use the extension and where we use the torsion of space, this torsion of space can accommodate something that we have in quantum mechanics and we don't have in the theory of relativity, namely the spin of particles. The spin of particles is a quantum property, and it manifests, pay attention, because of space. This is very interesting when you read about Dirac's equation in the theory of the relativistic electron, and then in the theory of special relativity and in quantum electrodynamics and so on. Because the spin is not an element of the electron added additionally by hand. No, not at all. In order to describe the spin, you have to start from the fact that the electron has 4 space states. 2 particle and 2 antiparticle states, electron and positron. And each of the 2, so there will be 4 in total, there will be spin up, spin down, spin up, spin down. But essentially there are 4 different states, which then act and function further due to certain laws. These include Lorentz transformations, spinor, and similar concepts, a very complex branch of mathematics. And after that you will see how the electron moves in a magnetic field. Yes, as if it has a magnetic moment, which is the magnetic moment associated with spin. The basic idea is that spin is a property of space, and this is also seen in the spin statistics connection. So the fact that after that half integer spins like 1/2, 3/2 are fermions, and the integer spins like 0, 1, 2, and so on are bosons. Alright, so spin is a property of space, and what the Einstein-Cartan theory does is introduce this torsion of space, which accommodates the spin property of electrons very well, so this quantum property. Alright, and now comes this Polish physicist who lives in America. Poplawski, who builds on this Einstein-Cartan theory and on the work of other physicists, of course, who conducted studies before him. And he says this: Sir, let's see what happens in the singularity of a black hole. What happens? Well, we have matter, right? Let's say during the explosion of a supernova, a stellar black hole forms inside the center of the supernova. Yes, how does a stellar black hole form? Well, it's because the matter that's there, that core of matter, can no longer withstand the gravitational forces. The gravitational forces are stronger than any force that could resist them. And after that it collapses toward the center. At some point when the matter collapses toward the center, the horizon forms around it of the black hole with a radius given by the Schwarzschild radius. So it is given by the amount of matter that has fallen in, which actually formed the black hole, yes. So the matter that fell inside. After that, the matter moves toward a singularity. According to Einstein's theory, at the singularity, at infinity, we don't know or understand anything. We can't say what's there. The Einstein-Cartan theory, so speaking of the physicist Poplawski, the Polish physicist, says, Sir, let's make these calculations much more precise. And let's do calculations not only based on the Einstein-Cartan theory, but also by adding some additional elements related to the pressure of that gas. Because we know the parameters of the stellar black hole before it collapses. And well, taking all these parameters into account, he says the following. Sir, the matter falls toward the center. But at some point, the matter, which is made up of fermions, so that means electrons, quarks, and so on, starts to get very crowded. And as it starts to get very crowded, what they have in their theory as the torsion of space, which is given by these spins, so by the particles with fermion spin, the torsion of space starts to play an important role in the Einstein-Cartan equations, and because of this additional torsion of space, a singularity will no longer form. In fact, on the other side, something similar to a white hole will form. So we will have something like an Einstein-Rosen type wormhole. On one side, a black hole, on the other side, a white hole. Attention, says Poplawski, this is not something that comes out, a white hole. It is something similar to a white hole, but it comes out of these Einstein-Rosen equations. And it's very important to stress, to say that it is similar to a white hole, because a white hole has a very strong curvature of space. And so, what comes out on the other side, if it is just a white hole, we should have a very strong curvature of space. But we do not observe a very strong curvature of space around us. We need a space that has a very small curvature of space. So something Euclidean, at least in these moments farther away from the Big Bang. Poplawski tells us, listen folks, so we have a black hole, matter falls inside. The singularity doesn't form because of the torsion of space. And then space somehow starts to expand in another direction, and there's something similar to a white hole forms. But actually, it's a new universe. It really is a new universe, because it will have a very low curvature of space. After a long time since the Big Bang, we will see an almost flat space, and in it, the initial matter will form a new universe. And that's the idea actually, that our Big Bang would actually be part of this universe. Let me get back, because I had written down a few ideas here and then I started talking a lot. So, Poplawski's idea is that the universe, which forms like a white hole, according to these brand new equations, would actually be our universe, because its curvature would be minimal. And the matter in that universe is given by the matter that existed in the previous universe where the black hole was. The first thing I thought was, well, wait a minute, that can't be. Because if such a universe forms, it has a lot of matter. Our universe has much more matter than would exist inside a star. Because as we've seen, that new universe would form with the matter that fell in. In the black hole, it would only contain the mass of a star. But pay attention, Poplawski tells us. If we solve the equations the way he did, I told you, I haven't looked at the exact equations, so I take him at his word. He says if we solve those equations, we would see that at the beginning of this new universe, yes, from this similar white hole that forms, we would see that there we discover what we call an inflaton field. That is for a short period of time. That new universe behaves just like our universe did at the beginning, because our universe at the beginning had a similar behavior, he says. The theory of inflation. At the beginning, right after the Big Bang, the mass of the entire universe would be, observably, the one we see in the sky. Yes, it would be approximately equal to the mass of an orange. So everything we see in the sky, that's what the theory of inflation says. Yes, everything we see in the sky could have come from the mass of a single orange. The theory of inflation also explains how this occurs, specifically through the inflaton field. After the Big Bang, an inflaton field appears, causing space to accelerate faster than light. But very importantly, and I also mentioned this in my physics stories, the energy density of that inflaton field remains constant. Whatever happens, if space expands and the energy density remains constant, well, the total energy increases. Energy is created out of nothing. Well, out of nothing. Some say it's not really out of nothing because you have to take into account the equations of the theory of relativity. And then you can find there a, so to speak, a kind of conservation law, in quotes, because others don't agree. They say you can't discuss a law of energy conservation, because then you have things that are dynamic in time. more than just dynamic. I mean, while time is dynamic, time changes. Then Noether's equation doesn't apply, which means that we need to have something that is conserved over time, and that something is energy. So essentially, it didn't contradict the laws of physics that the entire universe started from a mass just the size of an orange. That's what Poplawski is telling us as well, that it happened in that universe he constructed, that similar white hole, right? Its total mass would be about the same as the stars. But this, through this inflaton field, would have multiplied exponentially. After that, it would have created all the galaxies and stars we now see in the sky. And so our universe, says Poplawski, it is in fact a so-called white hole, in quotes, because it's different from the white hole described by Einstein's equations. A white hole that formed naturally from the collapse of a black hole? So somehow a new universe opened up, and that universe is us. And his arguments are as follows. 1, the calculations, the theory predicts this, which is a very good argument, right? 2, the calculations. The theory predicts that this so-called white hole will have one. The universe will be Euclidean, so space won't have significant curvature, just as we observe. Alright, at a certain time after the Big Bang. But 3, his theory predicts that we should observe a Schwarzschild radius for the observable universe we have, which is approximately equal to the limit of the radius at which the universe is observable, right? So the limit of the observable universe is the place where galaxies moving away beyond that limit are receding at a speed greater than the speed of light. That's the current limit of the observable universe. What is it now? About 40 to 45 billion light years. That's the radius of the observable universe. And the radius of the observable universe should be approximately equal to the Schwarzschild radius of a black hole, where we consider the mass of the black hole, attention, the mass of the entire universe. And, well, if you do the calculation, the two are approximately equal. And the third argument is what we're talking about today, says Poplawski. He says, hey, good people, well, after a universe was formed, that universe would have kept the rotational angular momentum that was in the initial black hole. Because most black holes that form, let's say in supernova explosions, gain an angular momentum, a rotational momentum, and that rotational angular momentum, says Poplawski, who once again did the equations, it is passed on through the torsion of space and all the elements it has in the next universe. And then, the next universe, after the Big Bang, would have a preferred direction of rotation. And that's what we see in the measurements from James Webb. We see how galaxies rotate in a preferred direction, opposite to the rotation direction of our own galaxy. Why is that? Says Poplawski. My theory is true. Look, pay attention, not in a black hole, but in a white hole. Which white hole was formed? Yes, beyond the center of the black hole. But indeed, our universe comes from a black hole, and actually an ordinary stellar black hole from another universe. Yes, so we can say that we appeared inside the black hole from another universe. We've reached the end. I'd like to add 2 things and wrap up. The first thing is related to Smolin's theory, the one about universes being generated inside black holes. Yes, Smolin essentially says the same thing that Poplawski says. That not only does our universe come from a black hole, possibly a stellar one, but it could also be a supermassive one from another universe. But if we look at the black holes we have here in our universe, in our galaxy, we have stellar black holes, and in the center of the galaxy, supermassive black holes. If we looked at them, then beyond them, we might see how a so-called white hole opens up, or rather another universe. In each, a new universe would be born. He calls this and also makes a connection with Darwin's theory of natural selection. Basically, a universe appears here, and that universe from this black hole. It has some initial conditions, and those conditions are so messed up that the respective universe, let's say, expands and then immediately collapses back. And that's the end of that universe. In another universe, again with very strange conditions, a universe comes out that expands and the particles don't get to form structures. In another universe. God knows what else happens and what could happen. It could happen that in one of these universes inside black holes, life-friendly conditions might emerge. And so says Smolin, the fact that we live in a universe where life could appear, it's not because there is a creator, it's because there is countless multiverses of other such universes, all appearing inside black holes from another universe. Wow, yes. And just as in Darwin's theory, the best organisms are selected, the same way here, the best universes in which life can appear would self-select. Alright, interesting if that's the case. I'll tell you at the end. And the second thing I want to tell you is that I watched the video about black hole cosmology, because what Poplawski is talking about is called black hole cosmology. The YouTube channel PBS Spacetime has a good video on black hole cosmology, although it doesn't mention many of the details that I just mentioned, so please watch it. But there at least I liked it. How does he detail this idea of a geodesic? The fact that in a black hole you go toward the singularity, yes, because that's where the future is, a geodesic inside the black hole. Matter moves toward the singularity not because it's attracted by the singularity, but because space-time is twisted. And I think my battery is going to run out. Let me talk like this, and you go toward the singularity because that's where the future is. Similarly, in a black hole, when you come out of a white hole, when you come out, yes, you go toward the future, which this time will be the exit. That's where the future and time are. That's why all the matter comes out of the white hole. And that's the similarity with the Big Bang. I'll stop because I think my battery is running out. Let me say the conclusion really quickly before it runs out. It's overwhelming. It's simply overwhelming. But I really like this idea that every time you discover something new, something completely surprising, indeed, there might be multiverses. Indeed, our universe could have emerged from a black hole. I haven't seen anyone say something like that. It's not impossible. It's possible. We just don't know yet. We need to make the measurements. It blew my mind. Dear friends, thank you for watching me. I'm looking forward to your comments on this new attempt, and don't forget, you're cool. All the best. See you next time.